Welcome to your next lesson of week 2. Here we're going to be talking about the derivative as a limit, and we're going to be doing homework from chapter 2, section 9. So, as always, if you have questions, make sure you put them either in the nomination form, in the comments, or you can just jump on and ask me a question on one of the appointments. Make sure you've got all your note-taking materials ready to go, and let's get started. So if you remember from last year, the definition of the first derivative of f of x is equal to a limit, and it's the limit as h approaches 0 of f of a plus h minus f of a all over h. And this is going to be a really helpful limit to know because it's going to help you recognize things that look like complicated limits, where you'd have to have remembered, the expansion of tan of a plus b, all these things, over h, in this case, where you actually don't have to worry about that as much if you remember that this is true. So this might be a problem that you see on a quiz or a test or even on the AP exam, and you can say, I recognize that as the limit form of the derivative because this is the same as the limit as h approaches 0 of tangent of pi over 3 plus h minus tangent of pi over 3, since root 3 is equal to tangent of pi over 3 all over h. And since I recognize that, that means that limit is the same as the derivative of tangent of x at x is equal to pi over 3, right? So that's what is in the place of a in this case. So if you recognize this, it just makes everything a little bit more streamlined. The derivative of tangent then, this is equal to secant squared of pi over 3. So again, we will go through these. If you don't remember your derivatives of every single thing you did last year, that is very understandable and quite expected. But if you do, it just can help you a lot. We will go through the derivatives starting with your next lesson, so that'll help as well. So if you do recognize it as a derivative and you do know the derivative, that's great. So here we can say secant squared of pi over 3. I will usually break that up to just secant of pi over 3 squared, which is the 1 over the cosine of pi over 3 squared. Cosine of pi over 3 is 1/2. 1 over 1/2 is 2. So this is 2 squared, so then my final answer for this whole limit is 4. One other thing that's really important to remember about derivatives and all these things, you're going to be asked about units and the effects of all of these things. For number 2, it says, a manufacturer produces bolts of fabric. There exists some function of the cost of producing X yards of fabric. C is equal to f of x, so the cost. So it says, what are the units of f prime of x? And this is where it's really helpful to remember that the derivative, or f prime, is the same as the rate of change. And that rate of change is of f of x over x. You can also think of this, and I'll be using this a lot, dy dx. This is called Leibniz notation, and I just find it a lot more helpful to do some problems in Leibniz notation than the Newtonian prime notation. And I know that that's something that's different than some of your former teachers. They're both fine. I won't mark points off. I just find this helpful because this is for the change in our y amount versus the change in our x amount. That d stands for delta, which if you're in science class you know means change. So what are the units of f of x, f prime of x? Well, if f of x units are measured as a cost, I feel safe assuming in the United States that's dollars, and the x units, as it says, are yards of fabric, then the units of f prime would be cost per yard of fabric. As I said, just a helpful way to think about it using the other type of notation. Here, interpret f prime of 1,000 is equal to 9. So once we know that that's what f prime is being measured in, what this says is that it costs $9 per yard of fabric when you are manufacturing 1,000 yards. So that's one way to summarize it in my words. As long as you're using your own logic and your own grammatical structure correctly, that'll be just fine. Just keeping your units and your variables organized. Lastly, I just want to talk about a limit that shows up a lot. It's not necessarily in forms of derivatives, but it's just a really helpful one. And that's the limit of sine of x over x as x approaches 0. So this is one that you will have seen when you talk about something called the squeeze theorem. And the way that you have seen this before is probably this idea of a sector drawn here where we have our theta, our angle, and we have theta cosine of theta, which is this arc length, sine of theta, which is the height, just think unit circle, and then theta itself, which is this outer radius here. And the reason that this inner one is theta cosine is because this distance here, this new radius, is cosine of the angle on the unit circle, and then we know out here is just 1. So that explains these 3 lengths. What we know based on this diagram, this section of the unit circle, is that x, cosine of x, this little one, is less than or equal to sine of x, this medium one, which is less than x, the outside. Now what we can do is we now have this inequality, and I'm going to divide everything by x, which I'm absolutely allowed to do, and then I'm going to take the limit of all of these together. And again, as long as I do the same thing to each part, that's fine. We know the inequalities will hold. Now, this limit on the inside is the one that we don't know, but we know the limit as cosine of x as x approaches 0 is 1, because that's just what cosine of 0 is. We know that limit as x approaches 0 of a constant is just itself, 1. So now we know that this limit must be in between 1 and 1, which means that it is also equal to 1. And you'll end up seeing this limit a lot in a lot of your calculus classes, and even more helpfully is that this is true even if you have a multiple for x. So right here, this is still true. If you have sine of a to the x over a to the x equals 1, you're going to see things like this quite a bit. So I know we jumped around a bit on this lesson, but please leave me any comments in the questions, nominate any problems you're stuck on, or get an appointment in the calendar to ask me there. Have a great day. I'll talk to you later.